Hello dear students, welcome back. In this video we are going to discuss about series solution of ordinary differential equation with the Frobenius series method, and particular when we have that the indicial roots of the indicial equation both are the equal, or we can say both are the repeated. So in that case its general solution will be what, and that we are going to discuss in this video. So let us start with the first. M is equal m1, these are the indicial roots of this particular indicial equation, and if you are going to get its solution c1y m is equal m1 and plus c2 del y by del m, and particularly we will replace y, m is equal, that is the m1. So in that case how to proceed with that we are going to understand with the particular equation. So let us start with x y double dash plus y dash minus y is equal 0, and that is a given differential equation. And clearly when I divide by x, and so in that case I will get that the x is equal 0 is nothing but singular point, and I also can verify that the x is equal 0 is a regular singular point. So check it. Therefore the Frobenius series method is applicable. So we have to assume that this is the general solution. So we can find y dash, y double dash, and now we are going to substitute all these values. So what I will get, let us see that here y double dash, so summation starting from that is 0 to infinite k plus m, k plus m minus 1, a k x raised to k plus m minus 2 plus y dash, that also you can see that k is equal 0 to infinite, that is k plus m, ak x raised to k plus m minus 1 minus summation starting from that is 0 to infinite ak x raised to k plus m is equal 0. Now I'm just taking the x inside, so what I will get, so summation starting from that is 0 to infinite k plus m minus 1, and ak is there, and x raised to k plus m minus 1, and this is there, that is the k is equal 0 to infinite k plus m ak x raised to k plus m minus 1 minus summation starting from that is 0 to infinite ak x raised to k plus m is equal 0. So now you can see that in the next step what we are going to consider to make the same power of x. So here x raised to k plus m1, m minus 1, these are the same. So I have to make that this is the k is replaced by k minus 1. So what I will get, this is the same. So I'm not going to change it. So this is the k plus m, this is the k plus m minus 1, ak x raised to k plus m minus 1, and this is summation starting from that is 0 to infinite k plus m ak x raised to k plus m minus 1, and here k is replaced by k minus 1, so k is equal 1 to infinite ak minus 1 x raised to k plus m minus 1 is equal 0. So here what we have to do to make the same power of x, that already we have done. Now we have to make the same index of the summation. That means we are taking here k is equal 0, also we are taking that k is equal 0, and then after the summation starting with k is equal 1 onwards. So let us see first k is equal 0. So what I am going to get, m times m minus 1 a0 x raised to m minus 1, and here you can see m times a0 x raised to m minus 1, then summation starting from 1 to infinite, and what I will get, so first I am taking that the k plus m common from these two terms, and after that we will have k plus m minus 1 plus 1, this is the ak is there, and minus ak minus 1 x times k plus m minus 1 equal to 0. So now you can see that for the indicial equation what we are taking, that lowest power of x, that is x raised to m minus 1 equal to 0. So x into m into m minus 1 plus m a0 equal to 0, But when I take a0 is non-zero, so what I will have m square minus m plus m is equal 0. So after simplifying, I will get m square is equal 0. So we have that the indicial roots m is equal, that is 0 and 0. So this is the real and repeated. So we have that this is the recurrence relation that also you can obtain because we have discussed about this one. So higher in terms of lower, so we will have ak minus 1 divided by k plus m raised to power 2, and this is valid for k is equal 1, 2, 3 onwards. So now just put here first k is equal 1. Now here we are going to discuss about its solution. For k m is equal, that is a 0 and again 0. So it is the repeated case. So first what we are focusing that first we will substitute k is equal 1, 2, 3 and so on. So this is for k is equal 1, k is equal 2, k is equal 3. So we are getting this one. So now I'm just substituting that ym. So it will be what? Ak x raised to k plus m, and from these k raised x raised to m summation k is equal 0 to infinite ak x raised to k is there. Now I'm just going to expand this one and substitute all these values that we have, the a1, a2 and a3 that you can write here. And after that I'm taking that the first solution when m is equal, that is the 0. So what I will get, a0 will be the common and x raised to 0, that will be the 1, and 1 plus x divided by 1 square plus x square divided by 1 square 2 square, and plus similarly we can extend x raised to cube divided by 1 square 2 square 3 square plus and so on. And also you can write that the 1 factorial 1 raised to power 2, so 1 factorial raised to 2, 1 into 2, this can be written as 1 into 2 raised to power 2, so that can be written as 2 factorial raised to power 2, this is the 3 factorial raised to power 2 and so on. And this is what our equation number A. Now let us move on to the next. Ym, this is we have that already we have written over here. Now what I'm just going to focus, now I want to find that the second solution, because the general solution is what? When we have the two, both are the repeated roots. So in that case, C1 ym is equal m1, and second says that you have to find the partial derivative of y with respect to m, and then we will replace by m is equal m1. So according to this condition, we have to find y in terms of m, and therefore we have started with that, and therefore we have this one. Now I'm just taking the partial integration, differentiation with respect to m. So I'm just taking this is the constant, and derivative of this one with respect to m, so it will be x raised to m ln x, and this is the same, so that is v plus x raised to m a0 is there, so I'm just taking the derivative of this one. So what I will get, this is the 0, and x divided by m plus 1 raised to power 2, but we know that y is equal 1 divided by x square is there, so its derivative will be what? Minus 2 times x raised to cube, and according to that I have minus 2x divided by m plus 1 raised to power 3. And here I'm just taking the product rule. How we can just look at here, this is the m1, and this, if I say this is the m square into n square, I'm just taking the partial derivative with respect to the same. So what I'm just taking that 1 divided by n square is there. So what about the derivative of this one? So I can say minus 2 divided by n cube plus what I'm just taking that 1 divided by n square is there, and again 1 divided by m square. So it will be minus 2 divided by m cube, and like that concept I'm just going to apply here. If I say this is the our m and this is going to be n, so in that case 1 divided by m square and minus 2 divided by n raised to cube, so m plus 2 raised to power 3 plus 1 divided by m plus 2 raised to power 2 is there, and derivative of 1 divided by m plus 1 square, that is a minus 2 divided by m plus 1 whole square into x square plus. Now let us write as a simplest form. This is there that we have written. X raised to m a0 is there. So minus 2x divided by m plus 1 raised to power 3. And whenever we combine, so minus 2 divided by what we are going to get the common m plus 1 square, m plus 2 square, that is the common, and we will have 1 divided by m plus 1, and again from this we are taking that m plus 1 is going to be there, and x raised to square plus and so on. So this is what our y2 del y by del m at m is equal 0, that means we are taking m is equal 0, and after simplifying we will get the required answer that you can see, and this is what our a0 ln x a0 is there 1 plus x divided by 1 square plus x square divided by 1 square to square plus and so on. And this is 2 minus 2 is a common, and a0 is also there, and x raised to 0, that is 1. So x divided by 1 raised to cube minus 2 already we have taken common, so it will be the plus 1 square 2 square into 1 divided by 2 plus 1 x square plus and so on. So therefore, but we have observed that this is what exactly our y1, so I have replaced over here, this is the y1, this is what our y2, this is the 2 times a0, that function that it is same, and say this is the second solution, that is the y2. Now I'm just taking the central solution and substituting all these value. So whenever we start with first solution, so C1 A0 with this, and whenever I consider the second solution, so in that case we have C2 A0, because this is what exactly C2 into A0 Y1 plus we have that another solution. So C2 A0 with Y1, so Y1 is nothing but this one, so that's why we have written over here ln x is there. Now that another C2 minus 2 times a0 is there, that already we have written over here, so I'm just replacing this one terms, so I will get this one. Also you can extend after this term, because 1 divided by 2 factorial raised to power 2 is there, so we can write 3 factorial raised to power 2, then 1 plus 1 by 2 plus 1 by 3 into x cube plus and so on. So this is what, this is arbitrary constant a, this is a constant b ln x, and this is the same again. This is going to be minus 2b, because C2 A0 is nothing but b, and this is the same that we have written, and this is what required series solution. So in this video we have discussed about that when the individual roots are equal, so in that case what will be the series solution with the help of the Frobenius series that we have discussed. Thank you.